Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we are continuing with our look into the reactions of alkenes and alkynes. Last lecture, we looked at how the carbon-carbon double bond of the alkene was susceptible to electrophilic attack. We defined what electrophiles were, looked at the mechanism of electrophilic addition reactions, and considered attack by hydrogen halides. We now want to look at hydration reactions that can occur in conjunction with alkenes and alkynes. If I take an alkene of this type, change my color back to blue. An asymmetric alkene, say as 1-propene, I can react this with a molecule such as H2SO4. And if I hit it with H2SO4, of course, the first thing I get that I would draw is the Markovnikov addition. I would produce the addition product with attack by acid. The electrophile H+ is attracted to the pi cloud. It adds Markovnikov to the carbon with the most hydrogens. And then we can get attack by H2SO4-. Now we saw the formation of such inorganic esters when we looked at alcohols. In other words, you can get attacking the carbocation, the addition of the H2SO4-. Now the H2SO4- is not a super powerful nucleophile, but it certainly can add. And you'd produce isopropyl hydrogen sulfate. Now, if you hit this with H2O and heat, water is a weak nucleophile. We have a very good leaving group. And the H2SO4- will leave and the water will attack, giving us CH3, CH, CH3, OH, H, positive. And then we can have the H2SO4- come in, or even water come in and grab the proton. So H2SO4- could come in, leave as H2SO4, and you end up with your isopropyl alcohol. What's interesting is we can go direct to this species if we use water with sulfuric acid. If instead of using pure sulfuric acid, we had thrown in water, And rather than holding it at 0 degrees, we let it react at room temperature. We can get substitution, and it might take a small amount of heat to get the alcohol. Okay, if instead of water I had used ethanol, let's give it a little more, or methanol, let's use ethanol. I would have gotten the protonated, which will very quickly go to the ether. So if instead of water you use alcohol, you get ether. Okay. This is referred to as the hydration reaction of an alkene. We can go through the hydrogen sulfate if we react first with pure sulfuric acid at low temperature, and then subsequently react with water. If you throw H2SO4 mixed with water, we will get the alcohol. Lastly, if we use an alcohol instead of water, we'll get an ether. The interesting problem with this reaction is that you'll note, wait a second, if I take alcohol and react it with sulfuric acid and heat, I get alkene. Well, if you remember that reaction from alcohols, you begin to realize that this reaction is in fact an equilibrium. The backwards reaction also applies, and that's why you can use heat for it as well. So because of this, yields are rather poor. That is, we don't get a lot of the alcohol because it is an equilibrium. The alcohol can react with the acid in the presence of heat to go back to the alkene. And so there's an equilibrium between the two. So if you use lots of alkene with sulfuric acid and water, you'll start generating appreciable amounts of alcohol. If you use lots of alcohol with H2SO4 and water and apply heat, you'll get appreciable amounts of alkene. And you just collect whichever one you want. The yields are not great. Also note, carbocations are involved here, so rearrangements do occur, and you have to watch for 1-2 shifting. An interesting reaction is what happens if we try a similar type of reaction with an alkyne. An alkyne. Suppose I use propine. And I throw it in some sulfuric acid. And I add some mercuric sulfate, HgSO4. Well, as you might expect, we actually get Markovnikov addition. H plus adds to the carbon with the most hydrogens, in this case the carbon of the triple bond. And if we do that, we'd get something like this. We get a positive charge. The mercury would associate with the positive charge. H2SO4, and of course there's water in this reaction. So sulfuric acid, mercury sulfate, H2O, eventually H2O attacks the positive, and you get this type of unit forming. Now, this molecule, I'm going to put it in brackets. It's not a transition state, but it is a bit unstable. It's referred to as an enol. Now, enols undergo a process called tautomerization. Tautomerization is a process in which you move a pi bond and one or more hydrogens. Now, what essentially happens when we do this tautomerization, and we can picture this quite nicely, and I'll draw the process for you. The lone pair in oxygen, I can draw a resonance structure. Tautomerization, though, is not resonance because we're shifting atoms. But I can draw a resonance structure like this and create a minor contributor that looks like this. It's a minor contributor because carbon has a negative charge. It's positive charge and electronegative oxygen. A lot of things wrong with this. But now I can start moving atoms. I can, for example, lose an H plus off the oxygen. If I do that, I get CH3, C double bond O, CH2 minus. And then I can very quickly pick up a proton where the minus was. Now you see, what we've done is we've put the proton where minus was and we got a ketone. This ketone and the enol are referred to as tautomers. Tautomers are structures found in solution that are equilibrium. They are not resonance structures. It turns out that the equilibrium is shifted very heavily to the keto form, not the enol form. And the reason is the stability of the C double bond O. It's much stronger. So all alkynes, when reacted with H2SO4, mercuric sulfate, and H2O, add to give you a ketone. The enol is only a short-lived intermediate. Now there is an equilibrium between the enol. There's always a trace concentration of enol in solution with the ketone. And these two are in equilibrium. They are not resonance structures of each other because you've moved atoms. You've moved atoms. You've not just moved the pi electrons, but you've taken a proton off and put a proton on. You've essentially shifted this hydrogen to the CH2 minus. Note that you get Markovnikov addition. The H plus adds to the carbon with the most hydrogens. You get H2O adding to produce the enol. And then tautomerization to make the ketone. And so, if I were to draw the product for this reaction, if it was given as a reaction, I would be expected to draw so if I gave this as my reagent, and the use of mercuric sulfate isn't required, but it does help. Mercury has a lot of electrons on it. If I give you this, the proper product, of course, is the ketone. You only get part marks if you give the enol. So you should give the ketone. Okay? So if you draw the enol, draw it on scrap paper, figure out what happens, follow your resonance arrows, move the protons around, and you can figure out which ketone you get quite easily. Okay. So that's hydration of an alkyne. What we want to do now is look at another reaction called Oxymercuration-Demercuration. Oxymercuration-Demercuration is a reaction that will produce an alcohol from an alkene. And of course, the first step is oxymercuration. Now, oxymercuration involves the preparation of an electrophile. An electrophile that attacks the alkene is a mercury atom. And it looks like it's derived from a mercuric acetate. Excuse me. Now, acetate is a C double bond O, CH3. What I've drawn here is the oxymercuration product, and we're preparing the reagent. If you dissolve mercuric acetate, mercury is 2 plus, acetate is 1 minus, so you have 2 of them. This will dissociate in solution to mercury with just 1 acetate on it. And it'll be positively charged. And of course the other acetate will be floating in solution. So there's a negative charge here. Okay. Now, the first step, oxymercuration as it's called. So let's remove the demercuration part from the title, because that's the overall name of the mechanism. This is step 1. And the first part, of course, so let's put a little 1 here. So oxymercuration begins with mercuric acetate dissociating into this very good electrophile. It's positively charged. It can accept 2 electrons. It's lost the acetate. It's dissolved as an ion, solvated in the aqueous solution or whatever solvent system you're carrying the reaction out in. And this electrophile will attack an alkene. So let's use an alkene, I don't know, like this guy. Now this electrophile will add Markovnikov. The mercury will add to the carbons with the most hydrogens. What's interesting though is mercury is a huge atom. It's found at the bottom of the periodic table, and as you go down in the periodic table, atomic radius increases, so you know mercury is a very large atom. And when mercury adds, you would think you would get a carbocation, a simple carbocation. You would think you'd get a positive here, and indeed one does. But it's not as simple as that, because if we got a simple carbocation, the first thing we'd have to do is watch for 1,2 shift, and I can see this is a secondary carbocation. If I shift this H over, I go to tertiary. But mercury is extremely large. It is a very, very large atom. And because of its large size and available electron clouds, those electron clouds are interacting with the carbocation carbon. It's almost like the mercury is bridging this unit. And the extra electron density that carbocation can receive from this large mercury atom being in close proximity stabilizes the plus. The plus stays near those electrons. And the mercury suppresses the 1,2 shift. It stops the 1,2 shift from happening. Essentially, the mercury stabilizes this carbocation so you don't make the tertiary. The mercuric oxidation step, or the oxymercuration step, prevents formation or prevents rearrangement. So what happens is the 1,2 shift doesn't occur, and because we're in water, we can have water act as a nucleophile on the positive. So water can come in and attack. And we'll get CH3. We still have our mercury and our OC double bond O CH3. Now this acetate over here, the CH3 CO2 minus if you like, that's in solution, can grab the proton. And it can go out as CH3 CO2H. If it grabs the proton, then we finish up the oxymercuration, having deprotonated our protonated alcohol. And we get the alcohol group, rather than the oxonium ion. We get the OH. But we still have this mercury on us. I'll put it up this time. With the OC double bond O, CH3 attached to it. So we still have the mercury group on here. So in step 1 oxymercuration, we add to the alkene, we prevent rearrangement, there's no 1,2 shifting, And we get the alcohol, but we still have the mercury. Now we need the second step called demercuration. Demercuration So let's draw our product again. This is step 2, demercuration. We have our CH3, C, CH3. We have our CHOH. We have this CH2, which has this mercury attached to it. And what we do is we hit this with a reagent. Sodium borohydride, and reduce the mercury to mercury metal. Now mercury metal is a liquid. It would settle to the bottom and you could collect it out of the system. It's not soluble. You could collect it as a metal out of the system using a SEP funnel in H2O and hydroxide. H2O and OH minus. What happens is you get mercury, but mercury metal is a liquid. And you get the alcohol. It works really nicely. And you get very good yields in this reaction. If in the original oxymercuration step, step 1, you had used instead of water, say methanol, you would have had an OCH3 here. So you can make ethers in the oxymercuration step, which would have ended up with an ether. So if you use an alcohol instead of water, you get ethers instead of alcohols. Make sure you take note of that. Okay. Well, this is a nice reaction because it occurs without rearrangement. So now we're set up quite nicely. I have to look for rearrangement when I get a carbocation. So if I have this alkene, and I hit this with H2SO4 and H2O, I know I get Markovnikov addition. I know that's going to give me a carbocation. I know I'm going to get a 1,2 hydrogen shift. And because of the tertiary carbocation, I'll get the OH going where that H was. I know I'll get this. But if I use 1 Hg bracket O2CCH3, that's the acetate, twice / H2O. Watch that. That H2O is crucial. If I use methanol here, I get an ether. And then 2, what was it? Sodium borohydride, H2O, hydroxide. This is oxymercuration-demercuration. It does the exact same thing except I don't get the shift. No 1,2 shift. Well, if there's no 1,2 shift, then the OH goes on here. So you can do either. So given our hydration reactions, preparation of alcohols, we now have enough ability to do reactions where we get the shifted alcohol, albeit it'll be in low yields because it's in equilibrium, or we can use oxymercuration-demercuration to prevent the 1,2 shift, prevent rearrangement, and get the unshifted alcohol. And granted, that is in excellent yields, high yields. Wouldn't it be perfect if we could just stick an OH on the very end of this molecule and get the antimarkovnikov? Too bad there wasn't a way to do that. Well, in fact, there actually is a way to do that. What do you mean? Well, it's called Hydroboration-Oxidation. Hydroboration-Oxidation. It turns out that the molecule diborane gas, B2H6, is a very good source of hydrogen. Also, it's a powerful electrophile because it allows us to get a Lewis acid. Remember, boron can have 3 groups around it. And having 3 groups around it, boron has an empty orbital and can accept electrons. Diborane gas, B2H6, is a very reactive molecule. It's like 2 BH3s stuck together. It ignites spontaneously in air, and it's tricky to make. You can make it by taking 3 sodium borohydrides, react them with 4 BF3s, you'll get 2 diborane gas molecules, B2H6, and 3 sodium tetrafluoroborates, 3 sodium BF4s. Now in ether, if you do this reaction in ether, as the B2H6 forms, because, as I said, these are 2 associated BH3s, and BH3s has empty orbitals, think of B2H6 as 2 BH3s that couple or join up together because of their empty orbitals. And ether has lone pairs on it, so ether can interact with the B2H6. So if you have diethyl ether, if you dissolve it in ether, you can get your ethyl groups, C2H5, your 2 ethyls, which are attached to your oxygen. Okay, you can get a lone pair interacting and solvating a BH3. And of course, as you might imagine, there are 2 of these. So ether solvates it and you get BH3. Well, here's where a hydroboration reaction starts. It's with the reactivity of BH3 itself. See, BH3 is like BH4 minus, which we've talked about earlier. Boron is one of the few elements less electronegative than hydrogen. It's a source of H minus. Also, the boron has an empty orbital. What do you mean? Well, let's consider the first step of the hydroboration reaction. So, step 1 is hydroboration. Our reagent, I've showed you how it's made, is BH3. And BH3 is a source of H minus, as well as being a powerful electrophile because he has an empty orbital and can accept electrons. So if we have our alkene, now let's use the same alkene as last time. And I have BH3. So here's our BH3. I'll put BH2 here. There is a delta plus on the boron and a delta minus on the hydrogen. Furthermore, the boron has an empty orbital that can accept electrons. Boron's an electrophile. Electrophiles add Markovnikov. The B part of the boron will add to the carbon with the most hydrogens. Now when the two electrons from the pi bond go towards the boron, this is going to create a positive charge on the carbon. And so the hydride takes its two electrons and puts them on carbon. And so what happens is you get an alkylborane. The H goes on the carbon, and the boron is on the CH2. Now what's interesting about this is the boron has two more hydrogens that are delta minus, and the boron still has an empty orbital, so it can do the same thing again to another alkene. It can react 2 more times. And if it does react 2 more times, you end up getting 3 of these groups around the boron. I'm going to say CH2 now, CH2. I'm going to put this in brackets and say 3 of them. All attached to boron. And the boron, instead of having any hydrogens, now has these alkyls. And they're called, this is a tri-alkyl. In this case, what's the name of that alkyl group? Common name, 1, 2, 3, 4, 5. Tri-isopentyl borane. Hydroboration makes a trialkyl borane. Well, the second step is called oxidation. In the second oxidation step, we can take the trialkyl borane and react it with peroxide. So we can take our CH3, CH3, CH2, CH2, 3 of them on the boron, And we hit it with peroxide and base, H2O2 and hydroxide. We react it with the peroxide and base. What happens is that the trialkyl borane gets oxidized, and where the Br, we get 3. What happens to the borane? The borane becomes borax, BO3 2-, borate anion. So the peroxide oxidizes the boron off and you get the alcohol. Note, you could have done several other things here. If we had used Br2 in hydroxide, if you use Br2 in hydroxide, you would have gotten 3 isopentyl bromides. So instead of putting an OH on, you could put a bromine on. What's nice is this is another route to antimarkovnikov addition of bromine. Last lecture we looked at antimarkovnikov by a free radical mechanism. Well, this one uses hydroboration-oxidation. We can even deuterate this position. Erase this. If instead of simple oxidation, we hit it with an acid, such as 3 acetic acids, but instead of having hydrogen, we use a deuterium in the position. If you use CH3, C double bond O, OH, use 3 of those, you would get 3 alkanes. Where it puts on an H. Now, if instead of using an H here, we used a deuterium, wow, that would have made a deuterated alkane. So in our oxidation step, we can prepare alcohols, alkyl halides, or even deuterated alkanes. Well, this really gives us a full spectrum of reactions in the preparation of alcohols. Hydroboration-oxidation occurs without rearrangement. It goes in high yield. It goes really nicely. And if we couple this with the previous reactions, we can make a nice summary sheet of the preparations of alcohols from alkenes. Using the same alcohol, or sorry, the same alkene. As stated previously, we can hit this with H2SO4 and water. If I do that, I will get rearrangement, 1-2 shifting, It is equilibrium, so the yields are not great. But I will get this alcohol. So what does the top reaction occur with? Well, we get poor yields because it's in equilibrium. It puts the H in what appears to be Markovnikov addition, so I'm going to go Markovnikov with this. It goes Markovnikov. The H plus adds to the carbon with the most hydrogens. And lastly, point 3, we get rearrangement. So we have to watch for rearrangement. Our next reaction is Oxymercuration-Demercuration. So one, we've got a mercury with 2 acetates off of it, O2C-CH3 twice. This dissociates in solution and reacts, and in the presence of H2O. Demercuration occurs in the presence of sodium borohydride. H2O and base. And so what do we get from this? Well, we get the alcohol but without rearrangement. There's no 1-2 shifting. We get Markovnikov addition, but yields are excellent. Okay? So if I'm to summarize this molecule, I would say 1, excellent yields. 2, still Markovnikov. The mercury added to the carbon with the most hydrogens. Looks like the H went on the carbon with the most hydrogens. And finally in 3, no rearrangement. No rearrangement. Our last reaction, our first step is hydroboration, and that requires BH3. So we just say BH3, usually dissolved in some kind of ether. And then 2, we use peroxide, H2O2, in base. The peroxide in base attacks the borate, and you get antimarkovnikov. Addition of the alcohol. So you get CH2, another CH2, and an OH. So if I compare this to what I got up, I'd say excellent yields. My second point would be anti-Markovnikov. The H looks like it went on the carbon with the least hydrogens. Now, granted that during the reaction, the boron really acts Markovnikov, but by the time you're done, it appears as if you added the H on the carbon with the least hydrogen. So we say antimarkovnikov. The reagent actually added by Markovnikov rules. But the electrophile wasn't H+, it was the boron. So by the time you take it off, it looks like the hydrogen went on the carbon with the least number of hydrogens. And the last point, again, no rearrangement. All right, so there you have it. We can make any alcohol we wish. Works out really well. And this reaction goes in high yields for both the oxymercuration and demercuration. So we're fully capable of getting any alcohol we want, including the antimarkovnikov product. So by knowing these reagents, you will be able to provide or prepare any of the desired alcohols, all three possibilities. Excellent. Okay. I think that's enough for now. What we'll do is continue next lecture with reactions of alcohols, and we'll move on and take a look at how polarizable molecules like Br2 and I2, etc. add to the double bond. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening.